Welcome back, everybody. Continuing our discussion. This one from winter 2018. The question here is, we have a reaction where a ketone gets reduced to a CH2. In our last segment, we briefly talked about that. And that is in chapter 16. And we find that Wolff Kischner reaction and Clemenson 16.3 M. And that will remove a carbonyl and make a CH2. The reaction involves an imine formation first, and then elimination, a tautomerization, then an elimination to form nitrogen gas. But you can look back at that section. Great mechanism. Students typically like it. This one, I do see that once again, we have this going on. And in our roadmap, the previous discussion, we saw that could be accomplished with H2 and PT. And that's called hydrogenolysis. That's found at the end of chapter 21. Hydrogenolysis. You want a section number. And a 21. We're looking for, well, not quite the end, huh? Well, look at me. I don't see it there. Oh, it's in the reactions at the benzylic position. So it's in 21.5. Perhaps our table of contents should be expanded. I would think that would help. But we're where we are. Hydrogenolysis is the name of that. There's also a removal of OH from this position and a hydrogen from a carbon one away. That's called dehydration of an alcohol. And we find that in chapter, let's see, that's a chapter 10 reaction where we talked about alcohols. We'll go find that too. And to do so, you need H2SO4 and heat. That's a 6. No. I'm thinking about hydration of alkenes to make the alcohol. The opposite is dehydration of the alcohol. That's chapter 10. Point. Dehydration, I think it's in 5. Let's see how bad my memory is getting nowadays. Let's do a quick look. Chapter 10 seems like 100 years ago. Dehydration of acid catalyzed dehydration of alcohols. Chapter 10.5 as promised. And there's that. And that would make this into this. And then she started her mechanism over here. Next up, we have some good questions today. A bunch of handwritten questions about aromaticity. Let's look at those one at a time. Fall 2019. We're talking about do the O's and OHs play any role in aromaticity? And the answer in these examples is no. This one's aromatic without the use of any of the O's, plus the O's aren't in the rings. So you don't entertain that option. Is the lone pair needed for aromaticity or not, unless the hetero atom is in the ring. And these pi bonds are not in the ring. So she talked about that. She talked about it. Since they are outside the ring, they have no effect. That is correct. You do not count those pi electrons when they are outside the ring. So you're only with 4 pi electrons here. And that's not going to cut it. And does N play a role in aromaticity here? No. Yes, the N can resonate with the benzene, but the benzene is aromatic all on its own without the N because it has the right number of pi electrons, 6. All right. Why this is not aromatic? Oh my goodness, it is aromatic. Why this is aromatic. And let's just take a look at it. It's got the right number of pi electrons. And I sure hope something I said on the answer key for fall 19 isn't saying this is not aromatic. I hope maybe it's just a interpretation of what I said. This is the situation where this atom, you need this lone pair to get up to the number 6. So you have to use it. The atom's in the ring. The question is, do you use it or not? And the answer is yes, because it gets you to 6 pi electrons. So it is aromatic. Now this would be the worst choice for putting a hydrogen on nitrogen here, because you've lost aromaticity in this molecule that used to be aromatic. You need to put the proton here so the molecule's still aromatic. Still aromatic. And it can resonate with the other nitrogen. When we have N+, it means it's no lone pair. That is correct. If you put a lone pair on this nitrogen, go ahead, see what happens on your test. You get OV -1 because you have 10 electrons around a nitrogen. Yeah, so this don't even draw that structure. Yeah, this is aromatic. This is where you would put the extra H on this nitrogen. And your aromaticity comes from these 6 electrons. You got the lone pair for 2, pi electrons for 2 more, pi electrons for 2 more, 6 pi electrons. Here you've only got 4 pi electrons. You lost your aromaticity because you put the hydrogen on the wrong nitrogen. Okay, here the minus is not considered 2 electrons. Oh, it sure is. That minus is a lone pair. It's a very unstable species, by the way. There it is. Now, ladies and gentlemen, you can't use both the pi electrons to resonate and the lone pair from the same carbon, one or the other. So you can't count these two and these two, because you're only resonating with one pair of electrons from any atom. So this thing for aromaticity has only 4 pi electrons, therefore not aromatic. If you're resonating this, then you can't be resonating this at the same time. And this one, yeah, well, we already discussed this one up here. There it is. Yes, this carbon is only using these 2 electrons for resonance, and it resonates into here. That's a terrible arrow. Resonates there. There are 5 resonance forms that are equally stable, so this is a remarkably stable anion. And there's 3 more. And this one, you're only resonating like this. And there's only, hey, how many arrows are there? You know, there's 2 arrows, 4 electrons, and you're getting this thing here. It's still got the same problem, you know. You can't use both of those. You can't get to 6. You can't do it. Why this is not aromatic? This is aromatic. It has everything we need. It has the right number of pi electrons. It follows all the rules. I'm just drawing it a little, not any different, just showing. I hope I got everything right here. Oh boy, I think I lost it. I need an extra carbon. That's a 7 ring down here. It's been a while since I've been tripped up by a 7. And we got that, and we got that, and I did it again. It's a 6. Doesn't look great. I made it trans too. It looks really bad. Okay. Kind of the same as what she's got. Yeah. Counting pi electrons. You use the lone pair if you need to. 2, 4, 6, 8, 10. 10 pi electrons, n equals 2. And it's aromatic. This is an sp2 carbon. It can resonate fully and freely with adjacent pi bonds. So it is aromatic, and the other resonance form is the more stable one. I think I got it finally. Look at that. No charges at all. How did I get there? You want to see how I got there? Here's how I got there. I resonated, let's see. I kept that one. I resonated this one down here. I resonated this one down here. And I resonated this one there. And I got there. Right here. And this one's easier to see. It's aromatic, right? 2, 4, 6, 8, 10. Don't have to ask the question, is there a lone pair needed for aromaticity? There's no lone pair. Do we have aromaticity in our next page? If not, yeah. This is about electrophilic aromatic substitution. We'll pick up from here. And we have until 9:30, so we've got time. Hopefully we get through all of our questions. I think we're going to do it. So see you in a bit.